Hello and welcome to the first in 3 short talks about shortcuts in circuit analysis, methods to avoid having to do a full nodal analysis, which can get quite algebraically tedious and complex. The first one is superposition. It's a technique we've seen before, and a reminder, it only applies to linear circuits. But when we can use it, it can save a lot of time. Let's do another example. This one. What is the voltage at point A? Well, we need to define all of the voltages at our nodes. So if that is point A, we'll define the point over here as being point B. There's a 2K resistor between them. There's also an 18 volt voltage source between them. We know there's a 4 milliamp current pumping up through here, and that there's a 3K resistor going down from B to ground. I'll take some of the shortcuts that I've talked about before. I won't define the current through this current source as a variable because I know it's just going to be 4 milliamps. So that leaves us with applying Kirchhoff's current law to node A, which would give us 4 milliamps equals the current through the 2K resistor. I'll call that I0 and this one I1. Their sum must be 4 milliamps. And I need to apply Kirchhoff's current law to this node, node B, which will tell me that I0 plus I1 is the current flowing down through the 3K resistor, which I'll call I2. But I know that I0 plus I1 is 4 milliamps, so I2 must be 4 milliamps, so I2 is 4 milliamps I can write directly. Then I have to apply the characteristic equations for each one of these components. There's no need to do it for the current source because I've already defined the current flowing up through here as being 4 milliamps. That's not a variable. I do need to apply Ohm's law to this 2K resistor, however, and that would tell me that VA minus VB, that's A minus B because the current is flowing in this direction from A to B, is I0 times 2K. And Ohm's law to this resistor, that would be VB minus 0, because that's ground, is I2 times 3K. And then this voltage source is telling me that VB minus VA is equal to 18 volts. And I've now got 5 equations in 5 unknowns. I0, I1, I2, VA, and VB. Start to solve. Okay, well, I know that I2 is 4 milliamps because I2 is I0 plus I1, and I0 plus I1 is 4 milliamps. So I could substitute that directly into here, and that would give me VB equals 4 milliamps times 3K, which is 12 volts. If VB is 12 volts, then I could put that into this expression here. 12 minus VA is 18. And that would give me that VA has got to be 12 minus 18, which would be minus 6 volts. So I've got VB and I've got VA. What about the currents? Well, I've got I2. I0 would come from this equation here. VA minus VB, well, that's just minus 18 volts. Because if VB minus VA is 18, then VA minus VB must be minus 18. So that's minus 18 equals I0 times 2K. So I0 is minus 9 milliamps. Which means the current is actually flowing this way through the 2K resistor. And that just leaves us with I1 to find. I1 is given by 4 milliamps minus I0, Well, I0 is minus 9 milliamps. 4 milliamps minus 9 milliamps would be 13 milliamps. So I1, 13 milliamps. And that's it. Solved. That's not too bad, but I would propose that it's actually easier to do it by superposition. By superposition, it would go like this. Take the circuit and set the voltage source to 0. Then, the circuit I've got is a current source of 4 milliamps flowing through the parallel combination of a resistor and a wire, because replacing a voltage source with a 0 voltage source means just replacing it with a wire. So all of this 4 milliamps is going to flow through the wire. None of it is going to flow through this resistor. We then have 4 milliamps flowing through a 3K resistor here, which would mean that the voltage there would be 12 volts, because that's 4 milliamps times 3K. Since this node here and this node here are currently connected by a wire, there will be no voltage difference between them, so the first contribution to my voltage at A is 12 volts. Next, I turn the current source off and I just consider the voltage source. If I do that, turning the current source off would mean replacing it with just an open circuit. So the circuit I would have, if I turn the current source off, is this. (2K, 18 volts). Now, for any circuit, the current going down to ground must come back up from ground somewhere else in the circuit. But there is nowhere else in the circuit for any current going down to ground to come back out of. This can't be part of any circuit, in other words, which means that there can be no current passing down through that 3K resistor. And if there's no current passing through the 3K resistor, there's no voltage across it, which means that the voltage at this point here would be 0 volts. This is an 18 volt voltage source, which is ensuring that the voltage here is 18 volts above the voltage here, which means the voltage here has to be minus 18 volts. That's our second contribution to the voltage at node A. Since the circuit is linear, I can use superposition and say that the result of both of these sources at the voltage A would just be 12 plus minus 18, which is minus 6 volts. Which is the same result as I got there, but I think that was a considerably easier way to get there. Much less likely to go wrong, no simultaneous equations to try to solve. We've seen superposition as a technique before. Reminder, it only works for linear networks, and a lot of networks that we'll be analysing are not linear, so we cannot use superposition. There are, however, a couple of other techniques that we can use, even with nonlinear circuits, provided parts of the circuit are linear. And we'll look at the first one of those in the next video.